boys and girls, it's Mrs. Leffler here, and I'm just going to give you a brief overview of absolute dating, also known as radiometric or radioactive dating. And absolute dating gives us a specific, as you can see in this picture right here, it gives us a specific year. Like this rock here is 120 million years, where when we did relative dating, it told us that this rock layer was younger than this rock layer underneath, and so forth. So that's what we're going to be looking at today. Our learning targets are going to be to understand radioactive dating, explain how to determine the absolute age of a rock or fossil, and compare and contrast the difference between relative and absolute age. All right, did you know that most of the organisms that have ever lived, 99% of them, are extinct? And so when we find fossils, and it's quite rare to become a fossil, it provides a historical sequence known as our geological time scale. And we're going to be looking at that time scale as we go on in the history of the Earth, all the way back to when it was formed. But we're going to teach you how they determine how old the rocks are and the fossils. So here is a picture of some fossils found in this sedimentary rock. Oops. As you can see, there are layers. I have 5 different layers here. And if we remember the law of superposition, the rock layer on the top will be younger than the rock layer beneath it. And so we can assume the same thing goes for fossils, that we can assume that this fossil is going to be younger than the fossils in the layers underneath it. And if you look closely, you can kind of examine that these fossils up here look similar to some of the shells that we might have found on the beach, and these down here might not be as recognizable. And so we could tell the relative age of these, but today we're going to try to figure out how to do the absolute age. So we're going to be using some radioactivity, so radioactive dating. And what do you think when you think of radioactivity? Do you possibly think of an atomic bomb? Do you think of something that could be very dangerous to you? Well, interestingly enough, radioactive atoms are all around us. So first, we're going to review a little bit about what an atom is. And you already know this. Here is a kind of a structure of an atom, a very simple diagram. And in the center is the nucleus, and around the outside in the cloud are electrons. And this one has protons and neutrons in the nucleus, like all atoms, and it has 3 protons and 3 electrons going around it. Those are the basic things. And you can determine the element by the number of protons. So what is radioactivity? Radioactivity is the process that an atom decays. So here is this uranium-238. It is not stable. So it's giving off stuff and it's releasing energy. It's releasing alpha particles, gamma particles, neutrons, protons, beta particles. And soon it's going to release enough that it'll end up being stable. So here's a term, isotope. An isotope could be an unstable reactive parent. An isotope basically means here's isotopes for carbon, carbon-12, carbon-13, carbon-14. They all have 6 protons, but to make it an isotope, they would have different neutrons. So this carbon-14 has 6 protons and 8 neutrons. So that's making it unstable. So here is what happens when radioactive decay takes place. You can see in this bottom example here, there's a parent isotope. It's very unstable. It will decay. It gives off energy, and that will turn into a more stable daughter isotope. Okay, so we're going to be talking mainly about carbon-14 because it has a pretty short half-life, and it's what we use to figure out the age of fossils. So all living things contain carbon-14. It's around us in trace amounts around us in the carbon dioxide. Plants take it in during photosynthesis, and so we breathe it in, and then we eat the plants, and it gets transferred into us. So here is this GNU. You can call it a wildebeest or a GNU, but a GNU is a lot more fun to say. And it's eating some carbon-14. It's got lots of carbon-12, but there is some carbon-14 found in it. And after it dies, it can no longer breathe or eat, so it's not taking in any more carbon-14. Now, when carbon-14 decays, the daughter isotope is known as nitrogen-14. And so that will be replaced. So you can take a look at the amount of carbon-14 and nitrogen-14 to figure out how old a fossil is. So we can estimate the age of fossils using radioactive dating. Rocks contain radioactive chemicals and break down. So there's a certain amount of time. It's pretty consistent with the way that it breaks down. It's predictable. So the amount of time that it takes for half. So here is this woolly mammoth, and it has all this carbon-14, and it's an unstable isotope. And so those are the parent isotopes. And so the amount of time it takes for half of those to be replaced by nitrogen, the nitrogen-14, this is showing N2 because that's a molecule. The amount of time is known as the half-life. And for carbon, for half of the original's amount to break down, it's 5,700 years. And so we can analyze that and figure it out. And I know this sounds a little complicated, but there is a video right here that you can watch. And you will be watching that to understand. And I did a little demonstration with M&Ms to explain half-lives to you. Now, all different chemicals have different half-lives. Carbon-14 has a half-life of 5,700 years. So after that amount of time, half of it will be nitrogen-14 and half will be carbon-14. And uranium-235 has a half-life of 713 million years. So if something was only 10,000 years old, this uranium-235 would not be a good element to test how old it is. However, if you wanted to test how old the Earth was, you probably wouldn't use carbon-14 because it wouldn't be reliable. There'd be such a small amount, we wouldn't be able to tell. So you would use something like uranium-235 to date older rocks like the Earth because it's 4.6 billion years old. Now, this man right here is going to explain that a little bit. It's an overview video for you. I'll let you look at that yourself. And then this is just basically you can test yourself. How old is that fossil? Test yourself. So if the initial amount of carbon-14 in a sample of a fossil is 16 grams and the half-life is 5,700 years, how much time has passed if there's 2 grams of C14 remaining? So you'll have to figure that out. Come back and look at this slideshow, this Google slide by yourself, and the answer is in the last slide. All right, thanks for listening.